Welcome to Triune Biblical University Global Extension USA channel. We are thrilled to welcome back our returning subscribers and extend a warm greeting to all our new viewers. Whether you're revisiting us for more knowledge or joining us for the first time, we're excited to have you here with us today. At Triune Biblical University Global Extension USA, we're dedicated to providing enriching educational content that empowers you to grow and excel. Your continuous support and engagement motivate us to bring you the best of our learning resources. Today's lecture, Advanced Structural Analysis. In today's session, we dive deep into the world of advanced structural analysis, a critical field for engineers and architects looking to push the boundaries of structural design and safety. Whether you're a student or a professional, this lecture will offer valuable insights into advanced methods and techniques that shape the way we analyze and design structures. So, sit back, relax, and prepare to explore complex concepts that will enhance your understanding of structural systems and their behavior under various forces and conditions. We hope you find today's lecture both informative and engaging. Let's get started. 1. Introduction to Advanced Structural Analysis. Overview of structural analysis. Structural analysis is the process of analyzing a structure's stability and behavior under various loads. This foundational concept is essential because it ensures the safety, performance, and longevity of the structure. Load types. Different loads affect a structure in various ways, and understanding these loads is vital. Dead loads, permanent forces like the weight of the structure itself, and live loads, variable forces such as people or vehicles, require different approaches for analysis. Environmental loads, such as wind, snow, and seismic forces, require more specialized methods, which we'll explore in dynamic structural analysis later in the course. For instance, the finite element method, FEM, and matrix methods are powerful tools to analyze the response of structures to these complex loads. Static versus dynamic analysis. In basic structural analysis, static equilibrium conditions, where forces and moments balance, are typically sufficient for simple structures. However, modern, more complex systems often require dynamic analysis, such as vibration analysis in buildings or bridges under seismic loads, as discussed later in the course. Structural behavior. The way a structure deforms, deflects, twists, bends, etc. under load is critical for design. Using advanced methods, such as FEM, we can visualize and calculate how structures deform in three-dimensional space, which is far beyond the capabilities of traditional analysis methods. Material properties. Every material has its own unique response to stress and strain, and understanding these properties is crucial. For example, steel and concrete behave very differently under load, and this must be factored into the analysis. Advanced methods allow us to model nonlinear material behavior, such as plasticity, discussed in the Plastic Analysis of Structures section, or time-dependent effects, like creep and shrinkage in concrete structures. Importance of advanced methods in engineering. As engineering projects become more complex, traditional methods often fall short in accurately predicting structural behavior. Advanced methods are required for the following reasons. Increased structural complexity. Modern buildings, bridges, and other infrastructure often include irregular geometries, complex loading conditions, and advanced materials, like composite materials. Traditional methods, like hand calculations, may not be practical or sufficient for analyzing these structures. Matrix methods, FEM, and plastic analysis help analyze these complex systems efficiently. Optimization. Advanced techniques allow engineers to design more cost-effective and resource-efficient structures. For example, finite element analysis, FEA, can optimize material usage, reduce weight, and improve safety margins. This is particularly important in tall buildings or bridges, where even small changes in design can lead to significant savings in cost and materials. Dynamic behavior of structures. In the course, we delve into dynamic structural analysis, which is essential for structures subjected to dynamic loads, e.g., wind, earthquakes, etc. Understanding the vibration modes and response spectrum of a structure under dynamic loading is critical for modern engineering. Advances in computational tools. The advent of software like SAP 2000, ATABS, and ANSYS has transformed how structural engineers analyze and design structures. These programs incorporate sophisticated advanced methods, like FEM and matrix methods, and provide engineers with the tools to model complex geometries and perform detailed simulations. In our course, we'll explore how these computational tools enhance structural analysis and enable the handling of very complex systems. Key concepts and terminologies. Here, we'll further expand on the concepts mentioned and explain how they connect to later parts of the course. Structural system. Understanding how individual elements, beams, columns, foundations, behave together is essential when analyzing a whole structure. In the matrix methods and finite element methods sections, we'll see how these elements are modeled mathematically and how their interactions are accounted for. Displacement. Displacements provide information about how a structure deforms under load. In advanced methods like FEM, displacement calculations are performed at many points within the structure, nodal points in the case of FEM, which allows for a more detailed and precise analysis. Displacement analysis is key for assessing structural serviceability, ensuring that a structure does not deflect excessively or experience unintended movements. Stress and strain. These concepts are central to the analysis of structural integrity. Traditional methods assume linear elastic behavior, but advanced methods allow for modeling of plasticity, nonlinear behavior, and viscoelasticity. As we move into sections like plastic analysis of structures, we'll explore how structures behave when they yield and undergo irreversible deformations, which is critical for understanding failure mechanisms and collapse behavior. Stiffness and flexibility. Stiffness describes the resistance to deformation, and flexibility is the inverse. In the matrix methods section, we'll develop the stiffness matrix for various elements of a structure and combine them into a global stiffness matrix that represents the entire structure. This matrix allows us to solve for displacements and internal forces. Understanding the relationship between stiffness and flexibility is crucial for designing efficient structures. Indeterminate structures. These structures cannot be fully analyzed using basic static equilibrium equations due to the lack of enough independent equations. As a result, advanced methods like the finite element method, FEM, and matrix methods are essential for solving these systems, particularly for large-scale and complex structures like high-rise buildings or bridges. Boundary conditions. The way a structure is supported or restrained, whether fixed, pinned, or roller, significantly influences how loads are distributed. Properly defining boundary conditions is essential for the success of matrix methods and FEM analysis. Without accurate boundary conditions, the analysis would produce incorrect results. Load paths. Understanding load paths is key to ensuring that the forces are effectively transferred from the structure's load-bearing elements to the supports. Advanced methods allow for a detailed understanding of these load paths in complex structures, especially in space frame analysis or truss analysis. connecting to later sections of the course. This introductory section lays the groundwork for the more advanced topics covered later in the course. 1. Matrix methods. After understanding the basic concepts of loads, displacements, and equilibrium, we will dive into matrix methods for analyzing complex structures, especially indeterminate systems. 2. Finite element method, FEM. Building on these principles, FEM offers an in-depth approach to breaking down structures into smaller, manageable elements for complex analysis, especially for structures that involve nonlinearities, large deflections, or variable material properties. 3. Plastic analysis. With the understanding of stress, strain, and material behavior, we'll explore how structures can behave in the plastic range, especially in situations of overload. 4. Dynamic analysis. The knowledge of displacement, boundary conditions, and load types will later help in understanding how structures behave under dynamic loads, e.g., earthquakes, wind, and how these forces influence structural behavior over time. 5. Computational tools. Finally, we'll move towards practical application in structural design using modern software tools, tying everything together for real-world, high-complexity problems. By the end of this course, you'll be equipped with both the theoretical understanding and computational tools necessary to analyze and design structures that meet the needs of modern engineering challenges. 1. Introduction to Advanced Structural Analysis. Importance of advanced methods in engineering. In modern structural engineering, the need for advanced analysis methods has never been more pressing. While classical structural analysis methods have been foundational, they often fall short in dealing with the complexities of contemporary engineering challenges. Advanced methods allow engineers to design safer, more efficient, and more cost-effective structures, especially in the face of increasingly complex demands. Let's explore why these advanced methods are essential in modern engineering. 1.1. Increased structural complexity. Modern structures, whether they are tall buildings, bridges, or industrial facilities, have become more intricate in design. Factors contributing to this complexity include irregular geometries. Modern architecture frequently features complex, nonlinear shapes that can't be modeled effectively using traditional methods. Curved surfaces, intricate facades, and non-conventional shapes demand more sophisticated analysis approaches, like the finite element method, FEM, which breaks structures down into smaller, more manageable elements. Mixed materials. The use of composite materials, such as reinforced concrete, carbon fiber, and glass fiber composites, requires careful modeling to understand how different materials interact and respond to loads. This often involves nonlinear material behavior, requiring advanced methods to simulate realistic performance. Large-scale projects. For large-scale structures like dams, bridges, or skyscrapers, the sheer number of elements involved makes manual calculations inefficient or even impractical. Matrix methods in FEM can handle large numbers of interconnected components quickly and accurately. 1.2. Need for precision and accuracy. Traditional structural analysis methods, while effective for simpler structures, often yield approximate solutions for complex systems. As the demand for higher precision increases, especially for projects that involve human safety and public infrastructure, more accurate and comprehensive analysis tools are required. Nonlinearities. Many real-world structures do not behave linearly under load, especially when materials yield or fail. In such cases, methods like plastic analysis and nonlinear FEM become necessary to capture the post-yield behavior and failure mechanisms of structures. Advanced load types. Modern buildings and infrastructures are exposed to a variety of loads that classical methods were not designed to handle. Dynamic loads, like earthquakes, wind forces, and traffic loading, temperature effects, or fatigue, need specialized methods to accurately predict the structure's behavior over time. Dynamic analysis, response spectrum analysis, and time history analysis help in understanding and designing for these complex scenarios. 1.3. Optimization and resource efficiency. In an era of growing environmental concerns and financial constraints, optimizing structural designs for both performance and resource use is crucial. Advanced methods allow engineers to minimize material use. FEM allows for the precise distribution of material across a structure. Engineers can optimize the thickness of walls, beams, or columns to use the least material while still maintaining safety and performance standards. Cost-effective solutions. By using advanced computational methods, engineers can avoid over-designing a structure, which leads to unnecessary material costs. Similarly, they can avoid under-designing it, which could result in failure or costly repairs down the line. Sustainability. Reducing material waste and ensuring a structure's longevity are crucial for sustainability. Using advanced simulation techniques ensures that the design is optimized not only for safety and functionality but also for environmental considerations. 1.4. Handling complex loading scenarios. In the past, structural analysis largely dealt with static loads, forces that remain constant over time. However, modern structures are often subject to a combination of static and dynamic loads, making the analysis much more complicated. This complexity requires more advanced methods, such as seismic and earthquake analysis. Buildings in earthquake-prone areas need to be designed to withstand dynamic forces generated by seismic events. Dynamic analysis and response spectrum analysis methods are crucial to understanding how buildings sway, deform, and dissipate energy during an earthquake. Wind and vibration loads. Wind loads on tall buildings, especially in areas subject to extreme weather, need to be analyzed using dynamic load models. Additionally, structures like bridges and high-rise buildings often experience oscillations and vibrations that can affect comfort and safety, which must be analyzed using specialized methods like modal analysis. Moving loads. Trusses, bridges, and other transport infrastructure need to handle varying loads from moving vehicles or trains. Advanced methods are required to analyze influence lines and moving load scenarios to ensure that the structure remains stable under changing conditions. 1.5. Enhancing safety and resilience. The safety of structures is paramount in engineering. As the complexity of structures increases, so do the risks associated with them. Advanced methods play a critical role in improving safety. Failure predictions. Advanced analysis techniques, such as plastic analysis and FEM, allow engineers to predict the point at which a structure will fail and under what conditions. This is especially critical for structures subjected to overloads or extreme conditions, such as bridges and dams. Risk assessment. Advanced structural analysis helps identify vulnerable points in a structure and allows for early interventions. This is especially crucial in seismic engineering, where performance-based design approaches help structures withstand anticipated ground movements. Resilient design. Structures that can resist extreme events, such as hurricanes, earthquakes, or fire, require advanced analysis methods to ensure they can continue to perform in the face of disaster. For example, advanced methods can simulate how buildings respond to extreme wind or how they perform under fire load conditions. 1.6. Computational tools and software integration. The rapid growth of computing power has revolutionized structural engineering, making it possible to analyze highly complex systems using software tools. Software like ANSYS, SAP 2000, and ETABS integrate advanced methods, e.g., FEM, matrix analysis, and nonlinear solvers, to provide engineers with powerful simulation tools. These tools enable automated analysis. Complex calculations can be performed quickly, which saves time and minimizes human error. This allows engineers to focus on interpreting results and making informed design decisions. Visualization. Software allows engineers to visualize how structures deform under different loading conditions, which is invaluable for detecting potential weaknesses or failure points before construction. Scenario testing. Engineers can test a structure's response under various conditions, e.g., changes in load, material properties, boundary conditions, without the need for physical models or expensive prototypes. This allows for more informed decision-making during the design phase. 1.7. Meeting regulatory and code requirements. With stricter building codes and safety standards being enforced globally, structural engineers must ensure that their designs comply with local and international regulations. Advanced methods are critical in code compliance. Software tools integrate design codes, like AISC, Eurocodes, and ACI, into the analysis process, ensuring that structures meet required safety and performance criteria. Performance-based design. Traditional design methods often focus on meeting code requirements based on load factors and safety margins. Advanced methods, however, enable performance-based design, where engineers can test a structure's actual behavior under realistic conditions, leading to more cost-effective and safer designs. In conclusion, the importance of advanced methods in engineering cannot be overstated. As structures become more complex, the variety of forces and conditions they are subjected to increases, demanding more sophisticated and accurate analysis tools. These advanced techniques, such as FEM, matrix methods, dynamic analysis, and plastic analysis, are indispensable for designing efficient, resilient, and safe structures that meet the needs of modern society. These methods not only allow engineers to deal with the complexity and scale of today's projects but also enable them to optimize performance, reduce costs, and increase safety. As we proceed through this course, we'll explore each of these advanced methods in more detail, equipping you with the knowledge and tools to tackle the challenges of advanced structural analysis. 1. Introduction to Advanced Structural Analysis. Key concepts and terminologies. Understanding key concepts and terminologies in structural analysis is crucial for grasping the advanced methods discussed throughout the course. These terms form the foundation for more complex analyses and guide engineers in designing and evaluating structures efficiently. Let's walk through the most essential concepts and how they connect to advanced structural analysis techniques. 1.1. Structural system. A structural system refers to the interconnected components or elements of a structure that work together to resist loads and maintain stability. These elements include beams, columns, slabs, foundations, and other structural members. The key characteristics of a structural system are load distribution, how loads, forces, are transferred throughout the system, from the point of application, e.g., a person walking on a floor, to the supports, e.g., the foundation. Types of structures. These systems can be classified as statically determinate, where forces and displacements can be calculated using simple equilibrium equations, or statically indeterminate, where the number of unknowns exceeds the number of equations, requiring more advanced methods like matrix methods and FEM. In advanced analysis, understanding how different parts of the structural system interact is crucial, and that's where methods like matrix analysis and FEM come into play, allowing engineers to analyze and design complex systems more effectively. 1.2. Displacement. Displacement refers to the movement of points on a structure due to applied loads. It's essentially how much a structure deforms, bends, stretches, twists, in response to forces. Displacement is crucial because it indicates serviceability. Excessive displacement can lead to serviceability issues, such as cracks in walls, non-functional doors, or windows that no longer align properly. In some cases, it may even compromise the building's aesthetics. Measures deformation. It's often used to assess whether a structure will remain functional under load or whether it will experience failure. For example, beam deflection under loading is one of the common displacement analyses done in structural design. In advanced methods like finite element analysis, FEM, displacements are calculated at numerous points, called nodes, across a structure to simulate real-world behavior with high accuracy. 1.3. Stress and strain. Stress is the internal resistance of a material to the external forces applied to it. It's defined as force per unit area, e.g., N/m squared or pascals. The formula is equals Fe equals F, where equals stress, in pascals, Pa, FF equals applied force, in newtons, N, A equals area, in square meters, m squared. Strain is the measure of deformation or displacement of a material in response to applied stress. It's the change in length divided by the original length. Equals LL equals LL, where equals strain, dimensionless. LL equals change in length. LL equals original length. In advanced structural analysis, these concepts are critical in understanding the material's behavior under load. For example, in plastic analysis or nonlinear FEM, structures may be analyzed beyond their elastic limit, where stress and strain are no longer proportional. 1.4. Stiffness and flexibility. Stiffness refers to the resistance of a structure or material to deformation under an applied load. A stiff structure doesn't deform much when forces are applied. Mathematically, stiffness is often represented as K equals Fk equals F, where P equals stiffness, FF equals applied force, equals displacement, deflection. Flexibility is the inverse of stiffness. A more flexible structure will deform more easily when forces are applied. In matrix methods and FEM, stiffness and flexibility matrices are used to describe how the structure deforms under applied forces. These matrices provide a way to mathematically model and solve for displacements and forces in complex systems. 1.5. Indeterminate structures. Indeterminate structures are those where the number of unknown forces or displacements exceeds the number of available equilibrium equations. Unlike statically determinate structures, where the system can be solved using just static equilibrium equations, indeterminate systems require advanced methods, such as matrix methods. These methods allow for the systematic solution of equations governing indeterminate structures. Finite element analysis, FEM. This method discretizes a structure into smaller elements, creating a system of equations that can be solved to determine the forces and displacements. Examples of indeterminate structures include most real-world buildings, bridges, and trusses, where advanced analysis is necessary to account for the internal force distribution and deformations. 1.6. Boundary conditions. Boundary conditions describe the constraints or support conditions that define how a structure is fixed or supported. These conditions are essential for determining how loads are distributed through the structure and solving for unknown forces or displacements. Common types of boundary conditions include fixed. The structure is constrained in all directions at the support. No displacement or rotation. Pinned. The structure is restrained from translation but can rotate. Roller. The structure can translate in one direction but is constrained in the perpendicular direction. Accurate boundary conditions are critical for performing an analysis, especially in advanced methods like FEM and matrix methods, where the behavior of the structure is dependent on how it is supported. 1.7. Load types. Understanding the different types of loads a structure may encounter is essential for accurately analyzing its behavior. These loads can be broadly categorized into dead loads, permanent loads that include the weight of the structure itself, e.g., beams, columns, floors. Live loads, variable loads such as people, furniture, vehicles, etc. Environmental loads, forces exerted by environmental factors like wind, snow, and earthquakes. Dynamic loads, time-varying loads that can include traffic loads or the effects of seismic events. These loads require dynamic analysis methods. Advanced methods like dynamic analysis or response spectrum analysis are used to understand how structures react under dynamic loading conditions, which are often not captured by traditional static analysis. 1.8. Load paths. A load path refers to the route through which external loads travel from the point of application, e.g., a weight on a beam, to the foundation or supports of the structure. Understanding load paths is essential for analyzing force distribution. In matrix methods or FEM, the load path is critical for determining how forces are transmitted through the structure and how different members are affected by those forces. Ensuring structural integrity. A well-designed load path ensures that all elements of the structure work together to resist loads without overloading any single component. 1.9. Plasticity and yielding. Plasticity refers to the permanent deformation that occurs in materials when they are loaded beyond their elastic limit. Once a material reaches its yield point, it will no longer return to its original shape after the load is removed. In plastic analysis, engineers study the behavior of structures when they undergo plastic deformation. This method is especially useful for analyzing structures that may experience overload conditions, as it helps predict failure mechanisms. 1.10. Energy methods. Energy methods are used in structural analysis to calculate displacements, internal forces, and other parameters based on the principle of work and energy conservation. These methods include Castigliano's theorems, used to compute displacements in structures based on the strain energy. Virtual work, a method for calculating displacements by considering the work done by internal and external forces. These energy-based approaches are particularly valuable for more complex analyses of indeterminate structures and can be integrated with advanced methods like matrix analysis and FEM. The key concepts and terminologies introduced in this section are the building blocks of advanced structural analysis. They provide the foundation for understanding how structures behave under various loading conditions and how engineers can use advanced methods to solve for forces, displacements, and other critical design parameters. As we move forward in the course, we will expand upon these terms by exploring specific advanced methods such as matrix methods, finite element analysis, FEM, and plastic analysis, which will allow us to solve complex real-world structural problems. 2. Review of classical structural analysis, static equilibrium and free body diagrams. Before diving into advanced structural analysis techniques, it's essential to review the foundational concepts of static equilibrium and free body diagrams, which are the backbone of classical structural analysis. These principles form the basis of many methods, both classical and modern, that engineers use to analyze structures. 2.1. Static equilibrium. Static equilibrium refers to the condition in which a structure is at rest or moving with constant velocity, meaning there is no acceleration. For a structure to be in static equilibrium, it must satisfy three fundamental equilibrium equations derived from Newton's laws of motion. These equations ensure that both the forces and the moments, or torques, acting on the structure are balanced, preventing it from moving or rotating. The equilibrium conditions are: 1. Force equilibrium in the horizontal direction. Fx equals 0, F equals 0, where F is the sum of all external forces acting in the horizontal direction. This equation ensures that there is no net force causing the structure to move horizontally. 2. Force equilibrium in the vertical direction. Fy equals 0, phi equals 0, where Φ is the sum of all external forces acting in the vertical direction. This ensures there is no net force causing vertical motion. 3. Moment equilibrium. About any point, typically the origin or a support point. M equals 0 equals 0, where is the sum of all moments, torques, about a chosen point. This equation ensures that there is no net rotational effect on the structure. These three conditions must be satisfied for any static structure in equilibrium. If any of these conditions are violated, the structure will experience movement or deformation. 2.2. Free body diagrams. A free body diagram, FBD, is a graphical representation of a structure or part of a structure, isolated from its supports and external forces, showing all the forces and moments acting on it. It's a crucial step in solving static equilibrium problems because it helps visualize the forces and moments that need to be considered in the analysis. The process of creating an FBD involves the following steps. 1. Isolate the part of the structure. Cut through the structure, if necessary, to isolate the part you want to analyze. You may need to break the structure into simpler components, such as individual beams, trusses, or sections of frames. 2. Identify and show all forces. External forces include forces such as applied loads, point loads, distributed loads, reactions at supports, and any other forces acting on the structure. Reaction forces. If a part of the structure is supported, e.g., a beam on a column, include the reaction forces at the support points. These can include vertical, horizontal, and moment reactions depending on the type of support. 3. Include moments. If the structure is subjected to bending or twisting, include moments in the diagram to account for rotational forces. The moment is usually denoted as when acts clockwise or counterclockwise around a point. 4. Label each force and moment. Every force and moment must be clearly labeled in the diagram. Typically, forces are shown as arrows pointing in the direction of action, with their magnitudes indicated. 5. Assume directions for unknown forces. If there are unknown forces or reactions, assume their directions, upward, downward, etc. If the assumed direction turns out to be incorrect, i.e., the value of the force is negative, you will know that the actual force direction is opposite to the assumption. Example of a free body diagram. Consider a simple beam supported at both ends, one end pinned and the other on a roller. The beam has a uniform load applied along its length and a point load in the middle. Step 1. Isolate the beam and remove the supports. Step 2. Identify and show the applied loads. The uniform load is shown as a downward arrow with a magnitude proportional to the load intensity, and the point load is shown as a downward arrow at the middle of the beam. Step 3. Add the reactions at the supports. Pinned support at the left and roller support at the right. The pinned support will have both a vertical and a horizontal reaction, depending on the beam's orientation, while the roller support will only have a vertical reaction force. 2.3. Solving for unknowns using static equilibrium. Once the free body diagram is complete, we can use the static equilibrium equations to solve for unknown forces or moments. For example, force equilibrium. Solve for unknown forces by applying the force equilibrium equations. Fx equals 0, equals 0 and Fy equals 0, phi equals 0. Moment equilibrium. Use the moment equilibrium equation, m equals 0 equals 0, to solve for unknown moments or reaction forces. By applying these equations systematically, we can determine the internal forces, shear, bending moments, axial forces, and displacements in the structure. Example problem: simply supported beam. Consider a simply supported beam with a uniform load and a point load acting at the center. We want to calculate the reactions at the supports. 1. Step 1. Draw the free body diagram, isolating the beam and showing all applied loads and reactions. 2. Step 2. Apply the force equilibrium equations. Fy equals 0, phi equals 0 to find the vertical reactions at the supports. M equals 0 to calculate the moments at one support and find the unknown reaction force at the other support. For example, if a uniform load was applied along the length of the beam and a point load PP is applied at the center, the reactions at the supports can be calculated using these equilibrium equations. 2.4. Applications of static equilibrium in free body diagrams. Trusses. In truss analysis, they're used to calculate internal forces in individual members using methods like the method of joints or method of sections. The equilibrium equations help determine the forces in the members of a truss that are in static equilibrium. Frames and arches. For more complex structures like frames and arches, help decompose the structure into simpler parts, allowing engineers to solve for internal forces and moments. By breaking down a frame into simpler components, each can be analyzed individually for forces and moments. Structural design. Static equilibrium and free body diagrams are fundamental in structural design for ensuring that all parts of the structure will remain in equilibrium under applied loads. This is essential for maintaining the safety and integrity of buildings, bridges, and other structures. 2.5. Limitations of static equilibrium. While static equilibrium provides the foundation for classical analysis methods, there are some limitations. Static assumption. Static equilibrium assumes that structures are not subject to dynamic forces, such as earthquakes, wind gusts, or traffic. For such cases, dynamic analysis is required, which accounts for time-dependent effects. Indeterminate structures. In statically indeterminate structures, where the number of unknowns exceeds the available equilibrium equations, classical static equilibrium methods alone are insufficient. In these cases, advanced techniques like matrix methods or finite element analysis, FEM, are necessary to solve the system. Static equilibrium and free body diagrams are fundamental concepts in structural analysis that form the basis for understanding the forces and moments acting on structures. These principles are not only crucial for simple systems but also serve as the foundation for more advanced methods, including matrix analysis, finite element analysis, and plastic analysis. Mastering these concepts is essential for any structural engineer, as they allow for the analysis and design of safe and stable structures. 2. Review of classical structural analysis. Methods of structural analysis: force, displacement, and energy methods. In classical structural analysis, several methods are used to solve for internal forces, displacements, and other parameters that govern the behavior of a structure. These methods have been developed over time and are fundamental to structural engineering. They can be categorized into force methods, displacement methods, and energy methods. Each of these methods has its specific applications and advantages depending on the type of structure being analyzed. 2.1. Force methods. Force methods are used to solve statically indeterminate structures by calculating unknown forces, reactions, or internal forces directly. These methods are based on the assumption that the number of unknown forces exceeds the number of static equilibrium equations available, so additional equations are required to solve the system. The general process for force methods involves selecting redundant variables. In statically indeterminate structures, there are more unknowns than available equilibrium equations. The force method starts by choosing one or more of these unknowns, called redundant, and removing them to make the system statically determinate. Solving the determinate system. Once the redundant forces are removed, the structure becomes statically determinate, and we can solve for the reactions and internal forces using equilibrium equations. Applying compatibility conditions. After solving for the internal forces, the next step is to apply compatibility conditions, which ensure that the deformations, displacements, of the structure are consistent with the assumed displacements. These conditions are used to find the values of the redundant forces by ensuring that the deformation of the structure is physically possible. Reintroducing the redundant forces. Finally, the redundant forces are reintroduced into the system to obtain the complete solution. Key features of force methods. Useful for analyzing structures like beams, frames, and trusses where the number of unknown forces exceeds the static equilibrium equations. The method requires knowledge of how the structure deforms under load, i.e., how forces are distributed. Example: in a continuous beam with supports that are not simply supported, force methods can help calculate the internal forces by introducing redundant supports and applying compatibility conditions. 2.2. Displacement methods. Displacement methods, also called stiffness methods, are based on the concept of solving for displacements, deflections, rather than forces. These methods are particularly useful for indeterminate structures and structures where the number of unknown displacements exceeds the available equilibrium equations. The displacement methods are based on the following steps. 1. Choose displacement variables. For structures that are indeterminate, the unknown displacements, such as rotations or translations, are chosen as the primary unknowns. These displacements are the degree of freedom in the structure, e.g., how much a point on the structure moves or rotates under loading. 2. Write the compatibility equations. These equations describe the relationship between displacements and forces. For example, if a beam bends due to an applied load, the displacement equation will relate the amount of bending to the applied forces. 3. Develop the stiffness matrix. The stiffness matrix is an important tool in displacement methods. It relates the applied forces to the displacements in the system. The stiffness matrix is used to represent the relationship between internal forces and displacements at the nodes of the structure. 4. Solve for displacements. Using the stiffness matrix and external load vector, the displacements are solved by solving the system of equations. 5. Calculate internal forces. Once the displacements are known, internal forces, such as shear forces, bending moments, and axial forces, can be calculated by using the structure's material properties and geometry. Key features of displacement methods. Displacement methods are more suitable for analyzing complex structures like frames, trusses, and high-rise buildings, where static indeterminacy is present. This method works particularly well for structures that have many degrees of freedom. Example: in a frame structure subjected to a load, displacement methods help calculate how much the frame deforms and then use this information to calculate internal forces. 2.3. Energy methods. Energy methods are based on the principle of work and energy conservation. These methods provide an alternate approach for calculating displacements, forces, and internal work done by forces on the structure. Energy methods are particularly useful when dealing with indeterminate structures, where both forces and displacements are unknown. The primary principles behind energy methods are: 1. Work energy principle. The work done by all external forces acting on a structure is equal to the change in its internal energy, strain energy, due to deformation. 2. Castigliano's theorems. Castigliano's first theorem states that the displacement of any point in the structure is equal to the partial derivative of the total strain energy with respect to the corresponding force. Castigliano's second theorem states that the internal force at any point in the structure is equal to the partial derivative of the total strain energy with respect to the corresponding displacement. 3. Virtual work method. The virtual work method is based on the concept that the work done by virtual forces, infinitesimally small forces, in a structure equals the virtual displacement caused by these forces. This method can be used to calculate the displacements in structures with more than 1 degree of freedom, such as frames or trusses. Key features of energy methods. Energy methods are often used for analyzing indeterminate structures, especially when other methods are difficult or time-consuming. These methods are useful for calculating deflections, internal forces, and moments in complex structures, especially when the system involves bending, twisting, or other nonlinear behaviors. Example: in the analysis of a cantilever beam with a load, energy methods can be used to calculate the displacement at the free end of the beam by calculating the strain energy and work done by the applied load. 2.4. Comparison of methods. Method. Type of structures. Advantages. Disadvantages. Force methods. Statically indeterminate beams, frames, trusses. Direct solution of internal forces. Requires careful selection of redundant forces and solving compatibility equations. Displacement methods. Complex frames, multi-degree freedom systems. Easy to implement using stiffness matrices. Good for large structures. Requires extensive computation. Matrix methods. May be complex for simple systems. Energy methods. Indeterminate structures with bending or twisting. Provides simple solutions for deflections and internal forces. Requires knowledge of strain energy and may be computationally intensive. 2.5. Applications of the methods. Force methods are used when solving for internal forces is the primary goal, and when there are only a few redundants to deal with. They are often used for simpler structures like beams with multiple supports or simple frames where the complexity is not high. Displacement methods are ideal for analyzing large and complex structures with many degrees of freedom, such as multi-story buildings, bridges, or any structure requiring a detailed analysis of how displacements relate to internal forces. Energy methods are often employed for structures that are hard to analyze using conventional equilibrium methods, such as structures subjected to dynamic loading or complex deformation patterns. They are also useful when we are particularly interested in the deflection and energy absorption of structures under loading. Force, displacement, and energy methods are fundamental approaches in classical structural analysis. While force methods focus on determining internal forces in statically indeterminate structures, displacement methods calculate the displacements and subsequently the forces in more complex systems. Energy methods, using the principles of work and strain energy, provide an efficient alternative for structures where forces and displacements are more difficult to solve for directly. Mastering these methods provides a solid foundation for approaching real-world engineering problems, and they are the basis for more advanced analytical techniques such as matrix methods and finite element analysis. FEM. 2. Review of classical structural analysis. Stiffness and flexibility matrices. In advanced structural analysis, the concepts of stiffness matrices and flexibility matrices are fundamental tools used to analyze and solve systems of equations that arise in structural problems. These matrices form the core of matrix methods of structural analysis, which allow engineers to represent the relationships between forces and displacements in a compact and systematic way. Let's break down these concepts to understand how they are used in the context of structural analysis. 2.1. Stiffness matrix. The stiffness matrix is a mathematical representation of how a structure resists deformation under applied loads. In structural analysis, stiffness refers to the resistance of a structure to displacements, i.e., how stiff or rigid the structure is under load. The stiffness matrix is essential for analyzing structures using displacement methods and matrix methods. Concept and definition. The stiffness matrix relates the displacements of the nodes or elements in a structure to the applied forces or loads. It is a square matrix where each element represents the relationship between a displacement at a particular degree of freedom and the corresponding force applied to that degree of freedom. In simple terms, the stiffness matrix tells you how much force is required to produce a unit displacement in a given direction. For each element, this matrix can describe how much force is needed to deform the element by a certain amount in each direction. The global stiffness matrix of a structure is the assembly of the stiffness matrices of individual elements, e.g., beams, columns, or trusses, in a global coordinate system. Formulation. For a simple 1D structural element, like a beam, the stiffness matrix can be derived from the material properties and geometry of the element. For a beam under axial load, the stiffness matrix might look like this. K equals E equals L, where E is the Young's modulus, material property. EA is the cross-sectional area. LL is the length of the element. In the case of 2D or 3D elements, the stiffness matrix becomes more complex, as it accounts for bending, shear, and torsion effects as well. For instance, for a truss element in 2D, the stiffness matrix for a linear truss element can be written as K equals EAL, COS, COSSIN, COSSIN, K equals L, cos 2, COSSIN, COSSIN, where E is the Young's modulus, EA is the cross-sectional area, LL is the length of the element, is the angle of the truss element with respect to the coordinate axis. Global stiffness matrix. When analyzing a structure with multiple elements, like a frame or a truss, the individual element stiffness matrices are assembled into a global stiffness matrix by applying the principle of superposition. The global stiffness matrix relates all the degrees of freedom of the structure to the applied loads. The global stiffness matrix KK is typically sparse, meaning many of its entries are zero. It is usually symmetric, and solving for the displacements involves inverting the global stiffness matrix. Q equals F, where KK is the global stiffness matrix, O is the displacement vector, FF is the force vector. Key features of the stiffness matrix. Represents the structure's resistance to deformation. Can be used to analyze structures under static loading. Force analysis. Can be extended to dynamic analysis when time-dependent loading is considered. Global stiffness matrix is built from individual element stiffness matrices using matrix algebra. 2.2. Flexibility matrix. The flexibility matrix is the inverse of the stiffness matrix. It represents the displacements produced in a structure due to the application of unit loads at each degree of freedom. The flexibility matrix is often used in force methods, also known as displacement-based analysis, where the primary unknowns are the forces in the structure, and the displacements are determined afterward. Concept and definition. The flexibility matrix provides a relationship between the forces and displacements in a system. Each element in the flexibility matrix indicates how much displacement occurs at a specific node or degree of freedom when a unit force is applied at another node or degree of freedom. Essentially, the flexibility matrix is used to analyze how easily or flexibly a structure can deform when subjected to loads. It tells you how much the structure will deflect under a given load distribution. Formulation. For a simple structural element, such as a truss or beam, the flexibility matrix can be derived from the stiffness matrix by inverting it. For a single element, if we have a stiffness matrix, the flexibility matrix is given by F equals K1, F equals K1. For more complex structures, the global flexibility matrix FF is derived similarly to the stiffness matrix, but it is often used to solve for displacements instead of forces. Global flexibility matrix. The global flexibility matrix is constructed from the flexibility matrices of individual elements, just like the stiffness matrix. The relationship for the displacement vector O is U equals Fu equals FF, where FF is the global flexibility matrix. FF is the force vector. O is the displacement vector. Key features of the flexibility matrix. Represents the deformation of a structure in response to applied forces. Often used in force methods, where forces are the primary unknowns. It can be used to analyze indeterminate structures that cannot be solved using only static equilibrium equations. The flexibility matrix is the inverse of the stiffness matrix. 2.3. Stiffness and flexibility in structural analysis. Stiffness methods. In the stiffness method, the displacement vector is solved for by using the global stiffness matrix. It is widely used because it works for a broad range of structural systems, and the resulting matrices are relatively simple to assemble using computational tools. Flexibility methods. In the flexibility method, forces are solved for by using the flexibility matrix. It is particularly useful in force-based analysis, such as when dealing with indeterminate structures where redundancy is present, and the solution is primarily sought in terms of forces. Both matrices are mathematically related and serve complementary purposes. The stiffness matrix focuses on calculating the structural response to applied forces, Displacements. The flexibility matrix focuses on calculating the response to applied forces in terms of displacements. 2.4. Applications in structural analysis. Stiffness matrix. Used extensively in finite element analysis, FEM, where large and complex structures are modeled and solved numerically. Helps in the analysis of frames, trusses, beams, and other structures subjected to static or dynamic loading. Useful in multi-degree of freedom systems where displacements are the primary unknowns. Flexibility matrix. Most effective in force-based methods, especially in statically indeterminate structures where the unknowns are internal forces. Suitable for analyzing displacement effects in systems with multiple redundancies, such as structures with complex boundary conditions or supports. Stiffness matrices and flexibility matrices are crucial components of advanced structural analysis. The stiffness matrix is used to relate displacements to forces, while the flexibility matrix is used to do the reverse. Both matrices form the core of matrix-based methods in structural engineering, facilitating the analysis of complex, indeterminate systems, and providing a systematic approach to solving structural problems. Understanding and using these matrices is essential for efficient and accurate analysis of real-world structures. 3. Matrix methods of structural analysis. Introduction to matrix methods. Matrix methods of structural analysis represent a powerful and systematic approach to solving structural problems. These methods involve the use of matrices to represent the relationships between forces, displacements, and other parameters in a structure. Matrix methods are particularly useful for analyzing large, complex, and indeterminate structures, where traditional hand calculations would be cumbersome and inefficient. By converting the equations governing the structure into matrix form, matrix methods allow for easy and efficient computational solutions, which are indispensable in modern structural engineering. 3.1. What are matrix methods? Matrix methods in structural analysis involve the use of matrices and vectors to represent the system of equations describing the behavior of a structure. These methods are grounded in linear algebra, and they provide a framework for solving systems of equations efficiently. A key advantage of matrix methods is that they allow for a systematic way to handle complex structural systems, such as trusses, frames, and beams, that would otherwise require lengthy and error-prone manual calculations. Matrix methods can be used to solve for nodal displacements, deflections, rotations, internal forces, bending moments, shear forces, axial forces, reactions at supports. Matrix methods typically make use of two primary matrices. 1. Stiffness matrix relates the applied forces to the displacements in the structure. 2. Force vector contains the applied loads or forces acting on the structure. The matrix equation that forms the foundation of matrix methods is Q equals F, where Kk is the global stiffness matrix of the structure. O is the displacement vector, unknown displacements at each degree of freedom. Ff is the force vector, applied loads or forces. The goal of matrix methods is to solve for the displacements O by manipulating these matrix equations. 3.2. Key concepts in matrix methods. 1. Degrees of freedom, DOF. The degree of freedom refers to the number of independent displacements or rotations that can occur in the system. For each node or element in a structure, we assign a degree of freedom to represent the potential displacements or rotations. For example, a truss structure has a degree of freedom for each node, typically translations in 2 or 3 directions. A frame may have degrees of freedom for both translation and rotation at each joint. Each degree of freedom corresponds to an entry in the displacement vector O. 2. Stiffness matrix. The stiffness matrix, KK, is used to represent the relationship between the forces and displacements in the structure. It is an essential element in matrix methods. The matrix is typically symmetric and square, with the size of the matrix corresponding to the total number of degrees of freedom in the structure. The stiffness matrix is developed from the stiffness of individual elements, beams, columns, trusses, and is assembled to create a global stiffness matrix for the entire structure. 3. Global versus local matrices. Local stiffness matrix. The stiffness matrix for an individual element, such as a beam or a truss, expressed in its local coordinate system. Global stiffness matrix. The matrix that represents the entire structure, expressed in a global coordinate system, e.g., for a building, it would be in the Cartesian coordinate system. The assembly process combines the local stiffness matrices of individual elements into the global stiffness matrix, based on the connectivity and boundary conditions of the structure. 4. Nodal displacements and forces. Once the global stiffness matrix KK is assembled, the matrix equation Q equals F is solved to find the displacements at each degree of freedom. The displacements vector O contains the translations and rotations at each node, or joint, in the structure. The force vector FF contains the applied forces at the same nodes. Once the displacements are found, they can be used to calculate internal forces and moments using the stiffness matrix. 3.3. The advantages of matrix methods. Systematic approach. Matrix methods provide a clear and systematic framework for handling large and complex structures, making them easier to manage and solve. Automation. Matrix methods are highly compatible with computational tools such as finite element software, e.g., ANSYS, SAP 2000, ATABS, which automatically assemble and solve these matrix equations. General applicability. These methods are flexible and can be applied to a wide range of structural systems, including trusses, frames, and even more complex systems like space frames or plate structures. Handling large systems. Matrix methods are particularly useful when solving large systems with many degrees of freedom, where traditional methods would be inefficient or impractical. Precision and efficiency. Matrix methods provide precise and efficient solutions to structural problems, reducing the likelihood of human error in calculations. 3.4. Basic steps in matrix methods. 1. Define the degrees of freedom. Identify the degrees of freedom for each node, or joint, in the structure. This includes the translational and rotational degrees of freedom. 2. Develop local element matrices. For each structural element, e.g., beam, truss, or column, develop the local stiffness matrix that represents the relationship between forces and displacements for that specific element. The local stiffness matrix depends on the geometry, material properties, and type of loading for the element. 3. Assemble the global stiffness matrix. The local stiffness matrices are then assembled into the global stiffness matrix for the entire structure. This process involves mapping the local degrees of freedom to the global system. 4. Apply boundary conditions. Apply boundary conditions, support conditions, to the global stiffness matrix. These boundary conditions reduce the size of the matrix and eliminate degrees of freedom that are constrained by the supports or fixed boundaries. 5. Solve the system of equations. Solve the matrix equation Q equals F to find the displacements at each degree of freedom. 6. Calculate internal forces. Once the displacements are determined, use the stiffness matrix to calculate the internal forces and moments in the structure, such as bending moments, shear forces, and axial forces. 3.5. Applications of matrix methods. Matrix methods are applicable to a wide range of structural analysis problems, including trusses. Analyzing internal forces in trusses by considering each joint has a degree of freedom and using the stiffness matrix to determine the axial forces in each member. Frames. Analyzing multi-degree of freedom frames, where both translations and rotations at each joint are considered. Space structures. Analyzing complex space frame structures, which require consideration of 3D displacements and forces at each node. Finite element analysis, FEA, the foundation of finite element methods, FEM, which subdivides complex structures into small, simple elements and applies matrix methods to analyze the global behavior. 3.6. Example of matrix method, truss analysis. In a simple truss analysis, the steps might look like this. 1. Define degrees of freedom. Identify the number of unknown displacements, translations, at each joint in the truss. 2. Develop local stiffness matrices. For each truss member, develop a 2x2 local stiffness matrix based on its material properties, cross-sectional area, and length. 3. Assemble global stiffness matrix. Combine the individual member stiffness matrices into a global stiffness matrix for the entire truss. 4. Apply boundary conditions. Apply the known support conditions, fixed or roller supports. 5. Solve for displacements. Solve the matrix equation to find the displacements of the joints. 6. Calculate internal forces. Once the displacements are known, compute the internal axial forces in each truss member. Matrix methods have revolutionized structural analysis by providing an efficient, systematic way to solve complex problems. The ability to handle large structures, incorporate various types of boundary conditions, and apply computational tools makes matrix methods a core part of modern structural engineering. Whether you're dealing with simple trusses or complex 3D frames, matrix methods are indispensable in obtaining accurate and reliable solutions. 3. Matrix methods of structural analysis. Stiffness matrix formulation. The stiffness matrix formulation is a central concept in matrix methods of structural analysis. It describes how a structure resists deformation when subjected to loads, and it plays a pivotal role in the displacement-based methods of analysis. In these methods, the relationship between forces and displacements is captured in the form of a matrix equation, allowing for efficient analysis of structures, especially those with multiple elements and complex geometries. In essence, the stiffness matrix relates the displacements of the structure to the applied forces. The goal of the stiffness matrix formulation is to systematically derive the stiffness matrix for a given structure or structural element, and then assemble it into a global stiffness matrix for the entire structure. 3.1. Key concepts in stiffness matrix formulation. 1. Displacement and force relationship. For a structure under load, the fundamental relationship between displacements and forces can be expressed as Q equals F, where Kk is the stiffness matrix of the structure, or an element. O is the vector of displacements, translations and/or rotations. Ff is the vector of applied forces or loads. The stiffness matrix Kk represents the structure's ability to resist deformations under applied forces, and its elements depend on the material properties, geometry, and boundary conditions of the structure. 3.2. Stiffness matrix for structural elements. The stiffness matrix can be formulated for individual structural elements, e.g., beams, trusses, columns, and then assembled to form the global stiffness matrix for the entire structure. 1. Stiffness matrix for 1D truss element. A 1D truss element is the simplest structural element. It has only axial stiffness and no bending or shear stiffness. The stiffness matrix for a 2-node truss element, with axial deformation, is derived from the relationship between the axial force and axial displacement. For a truss element with length LL, cross-sectional area AA, and Young's modulus E, the stiffness matrix in local coordinates, considering axial deformation only, is K equals EAL. 1st January 11, K equals Li 1, 1, 11, where E is the Young's modulus of the material. AA is the cross-sectional area of the element. LL is the length of the truss element. This matrix represents the force-displacement relationship for the truss element. For a truss element in a 2D coordinate system, the stiffness matrix is modified to account for the angle between the truss element and the coordinate axis. K equals EAL. COS, 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 SIN, COS, SIN, SIN, COS, SIN, SIN, COS, COS, SIN, COS, COS, SIN, SIN. K equals Li cos 2 cosin, cos 2, cos sin, cos sin, sin 2, cos 2, cos sin, cos, cos sin, sin 2 cosin sin 2, where is the angle of the truss element with respect to the coordinate axis. This matrix represents the force-displacement relationship in the global coordinate system for a 2D truss element. 2. Stiffness matrix for beam element. For a beam element with bending stiffness, the stiffness matrix accounts for both axial deformation and bending. The typical beam element in 2D has 4 degrees of freedom per node, 2 translational displacements in the x and y directions, and 2 rotational displacements about the x and y axes. The stiffness matrix for a beam element in bending, Euler-Bernoulli beam theory, is formulated as beam equals EL3, 126L, 126L 6L4 L2, 6L2 L2 minus 12, 6L12, 6L 6L2 L2, 6L4 L2, beam equals L3A 126L, 126L 6L4 L2, 6L2 L2 minus 12, 6L12, 6L 6L2 L2, 6L4 L2, where E is the Young's modulus of the material. 2 is the second moment of area, also known as the area moment of inertia. LL is the length of the beam. This matrix is used for analyzing bending and rotational effects in beam elements, and it can be extended to higher dimensions, 3D beam elements, for example, by including torsional effects and shear deformations. 3. Stiffness matrix for 2D frame element. A frame element includes both axial stiffness, like a truss, and bending stiffness, like a beam. The stiffness matrix for a 2D frame element can be represented as a 6x6 matrix, 3 degrees of freedom per node, accounting for both translation and rotation at each node. Frame equals EL 0, EL 0 0 0 12 EL 36 EL 20, 12 EL 36 EL 206 EL 24 EL 0, 6 EL 22 EL 0 EL 0 0 0, 12 EL 3, 6 EL 2012 EL 3, 6 EL 206 EL 22 EL 0, 6 EL 24 EL. Kframa equals Leah 0, Leah 0 0 12 L3 A 6 L2 A 0, 12 L3 A 6 L2 A 0 6 L2 A 4 Lay 0, 6 L2 A 2 Lay, Leah 0 Leah 0 0, 12 L3 A, 6 L2 A 0 12 L3 A, 6 L2 A 0 6 L2 A 2 Lay 0, 6 L2 A 4 Lay, where E is the Young's modulus of the material. A is the cross-sectional area. 2 is the second moment of area. LL is the length of the frame element. This matrix considers both axial deformation and bending deformation and is commonly used for analyzing frame structures, e.g., buildings, bridges. 3.3. Assembling the global stiffness matrix. Once the local stiffness matrices for individual elements, e.g., trusses, beams, frame elements, are formulated, they must be assembled into the global stiffness matrix for the entire structure. The process of assembly involves placing each element's stiffness matrix in the appropriate position within the global matrix, based on the connectivity between the elements and their degrees of freedom. Steps in assembling the global stiffness matrix. 1. Identify degrees of freedom. Assign a degree of freedom to each node in the structure. 2. Place local stiffness matrices. For each element, place the local stiffness matrix into the global stiffness matrix based on the degrees of freedom of the nodes that the element connects. 3. Sum contributions. If multiple elements share a node, sum the contributions from all elements connected to that node. The result is a sparse global stiffness matrix that represents the entire structure's response to applied forces. 3.4. Solving for displacements and forces. Once the global stiffness matrix is assembled, the system of equations Q equals F can be solved for the unknown displacements O by using standard linear algebra techniques, such as Gaussian elimination or matrix inversion. Once the displacements are known, the internal forces and moments in the structure can be computed by substituting the displacements back into the stiffness matrix. The formulation of the stiffness matrix is a crucial step in matrix methods of structural analysis. It allows engineers to systematically analyze structures, especially complex systems with multiple elements, by using matrices to relate forces and displacements. Understanding how to formulate and assemble the stiffness matrix for various structural elements, trusses, beams, and frames, is fundamental for using matrix methods effectively in solving real-world engineering problems. 3. Matrix methods of structural analysis. Assembly of global stiffness matrix. The assembly of the global stiffness matrix is a crucial step in the application of matrix methods for structural analysis. Once the local stiffness matrices for each structural element, such as beams, trusses, or frames, are formulated, the next task is to assemble them into a global stiffness matrix that represents the entire structure. This global stiffness matrix relates the displacements at each degree of freedom, DOF, of the structure to the applied forces. The assembly process involves systematically combining the individual stiffness matrices for each element based on their connectivity, i.e., which nodes they share. The result is a global stiffness matrix that can be used to solve for the displacements and internal forces in the entire structure. 3.1. Key concepts in assembly of the global stiffness matrix. The global stiffness matrix represents the overall behavior of the structure, and its size depends on the number of degrees of freedom, DOF, in the entire structure. Here are the key steps involved in assembling the global stiffness matrix. 1. Identify degrees of freedom, DOF. Each node in the structure has a set of DOFs, which represent the displacements, translations and rotations that can occur at the node. For a 2D frame, each node typically has 2 translational DOFs and 1 rotational DOF. The number of DOFs for the entire structure will be the sum of the DOFs for each node. 2. Formulate local stiffness matrices. For each element, truss, beam, frame, etc., a local stiffness matrix is derived that relates the forces and displacements for that specific element. The local stiffness matrix is typically small, e.g., 2x2 for trusses, 4x4 for beams, 6x6 for frame elements in 2D, depending on the number of DOFs per node. 3. Determine element connectivity. Each element in the structure connects a pair of nodes. The connectivity information indicates which DOFs belong to which nodes for each element. 4. Assign local stiffness matrix to the global system. The local stiffness matrix needs to be mapped into the global stiffness matrix based on the degrees of freedom corresponding to the nodes the element connects. The local stiffness matrix is placed into the global stiffness matrix at the appropriate positions corresponding to the nodes it connects. 3.2. General steps for assembling the global stiffness matrix. Let's break down the process of assembling the global stiffness matrix. 1. Labeling the degrees of freedom, DOFs. Each node in the structure has associated DOFs. For a 2D frame structure, the typical DOFs at each node might be translation in the x direction, translation in the y direction, and rotation about the z-axis. For example, for a structure with nodes, the global stiffness matrix KK will have 3n rows and columns, since each node has 3 DOFs in a 2D structure. The DOFs for the nodes might be labeled as follows. Node 1, U1, translation in 10, U2, translation in Y, U3, rotation. Node 2, U4, translation in 10, U5, translation in Y, U6, rotation, etc. 2. Formulating the local stiffness matrix for each element. For each element, e.g., truss, beam, frame, formulate the local stiffness matrix that relates the forces and displacements for that element. For example, truss element, a 2x2 matrix for axial deformation. Beam element, a 4x4 matrix for bending and axial deformations. Frame element, a 6x6 matrix that accounts for both bending and axial deformations. In 2D, each local stiffness matrix will have dimensions corresponding to the number of DOFs for the nodes it connects. For a frame element, for instance, the local stiffness matrix will be a 6x6 matrix for a 2D structure with 2 nodes, each node having 3 DOFs. 3. Mapping local stiffness matrices into the global stiffness matrix. Now, we need to map the local stiffness matrix for each element into the global stiffness matrix. Each element connects 2 nodes, and each node has several degrees of freedom. Therefore, the positions where the local stiffness matrix is placed in the global stiffness matrix depend on the node connectivity. For a truss element connecting node 1 and node 2 with axial stiffness, the local stiffness matrix might look like this. Clocal equals EAL, 1st January 11, Clocal equals Li, 1, 11, Here, EA is the axial stiffness, and LL is the length of the truss element. The degrees of freedom for each node are U1, U1 and U2, U2, corresponding to translations in the X and Y directions. When assembling into the global stiffness matrix, you place this local stiffness matrix in the positions of the global matrix that correspond to the degrees of freedom of the two nodes connected by the element. For example, if the element connects node 1 and node 2, you would place the local stiffness matrix into the global stiffness matrix at the following positions. Global equals KLOCAL. Global equals KLOCAL. 4. Assembly process for multiple elements. If the structure has multiple elements, you repeat the process of placing each element's local stiffness matrix into the global stiffness matrix based on its node connectivity. The global stiffness matrix is constructed by adding the contributions from all elements. For each element, you place its local stiffness matrix in the appropriate position of the global stiffness matrix, summing the contributions for shared DOFs. For example, if an element contributes to the force-displacement relationship for DOFs U1, U1, U2, U2, U3, U3, and so on, the corresponding entries in the global stiffness matrix are incremented by the local stiffness values at those positions. 5. Handling of boundary conditions. After assembling the global stiffness matrix, boundary conditions, such as fixed supports, are applied. If a node is fixed in a particular direction, e.g., translation in the X direction, the corresponding entries in the global stiffness matrix are modified, and the corresponding entries in the displacement vector are set to 0. Boundary conditions are often applied by eliminating the rows and columns corresponding to fixed degrees of freedom for a fixed displacement, or applying a large number, in some numerical methods, to represent a fixed displacement. 3.3. Example of assembly process. Example: simple 2D truss structure. Consider a simple 2D truss with two elements. Element 1, a truss between node 1 and node 2. Element 2, a truss between node 2 and node 3. Each element has 2 degrees of freedom per node. The displacements in the X and Y directions. 1. Local stiffness matrices. Formulate the local stiffness matrices for each truss element. Element 1. Stiffness matrix for the truss connecting node 1 and node 2. Element 2. Stiffness matrix for the truss connecting node 2 and node 3. 2. Global stiffness matrix. Assemble the global stiffness matrix for the entire truss structure by placing each element's local stiffness matrix into the global matrix based on its node connectivity. 3. Apply boundary conditions. If node 1 is fixed, both displacements are 0. Remove the corresponding rows and columns from the global stiffness matrix. 3.4. Solving the system. Once the global stiffness matrix is assembled, along with boundary conditions, you can solve the system of equations. Q equals F, where KK is the global stiffness matrix, O is the vector of displacements, FF is the vector of applied forces. Using standard numerical techniques, such as Gaussian elimination, matrix inversion, or iterative solvers, you can solve for the unknown displacements. The assembly of the global stiffness matrix is a crucial step in matrix methods for structural analysis. By systematically combining the local stiffness matrices of individual elements, engineers can model complex structures and solve for displacements and internal forces. This process is particularly useful for large-scale, indeterminate structures that require computational tools to analyze efficiently. 3. Matrix methods of structural analysis. Solving linear systems for structural displacements. Once the global stiffness matrix has been assembled and boundary conditions applied, the next step in structural analysis is solving the system of equations to find the displacements of the structure under the applied loads. This step involves solving a system of linear algebraic equations that relate the global stiffness matrix, the displacement vector, and the applied force vector. The general equation governing the displacement response of the structure is Q equals F, where Kk is the global stiffness matrix, square matrix of size n times n, where n is the total number of degrees of freedom in the structure. O is the displacement vector, column vector representing the displacement of each degree of freedom. Ff is the force vector, column vector representing the applied loads at each degree of freedom. The goal is to solve for O, the displacement vector, which tells us how much each degree of freedom in the structure moves under the applied loads. 3.1. Solving the system using direct methods. In direct methods, we solve the system of equations using standard linear algebraic techniques. The most commonly used methods are Gaussian elimination, LU decomposition, and matrix inversion. 1. Gaussian elimination. Gaussian elimination is a step-by-step procedure for solving a system of linear equations. The method involves transforming the system into an upper triangular matrix, then using back substitution to solve for the unknown displacements. Steps involved in Gaussian elimination. 1. Formulate the system Q equals F. 2. Perform row operations to create an upper triangular matrix. The goal is to eliminate the variables from the lower rows. 3. Back substitution. Once the system is in upper triangular form, solve for the unknown displacement starting from the last equation and working upwards. While Gaussian elimination is conceptually simple, it is computationally expensive for large systems with many degrees of freedom, DOFs. For very large structures, other methods like LU decomposition are preferred. 2. LU decomposition. LU decomposition is a more efficient method that decomposes the global stiffness matrix Kk into the product of two triangular matrices, K equals LUK equals LU, where LL is a lower triangular matrix, UU is an upper triangular matrix. After performing LU decomposition on the stiffness matrix, the system of equations Q equals F is solved in two steps. 1. Solve y equals F for the intermediate vector y. 2. Solve O equals Y for the displacement vector O. LU decomposition is particularly useful for large, sparse systems and can be more efficient than Gaussian elimination for these types of problems. 3. Matrix inversion. In some cases, we can solve for the displacements by directly inverting the global stiffness matrix. U equals K1 Fu equals K1 F. However, matrix inversion is computationally expensive, especially for large structures. It requires N3 operations for an n times n matrix, making it less efficient than other methods like Gaussian elimination or LU decomposition for large problems. 3.2. Solving the system using iterative methods. For very large structures, especially those with many degrees of freedom, iterative methods are often preferred. Iterative methods are particularly useful for sparse matrices, where many elements of the matrix are zero, and large systems where direct methods would be computationally expensive. The two most common iterative methods are 1. Conjugate gradient method. The conjugate gradient, CG, Method is one of the most widely used iterative methods for solving systems of linear equations where the stiffness matrix Kk is symmetric and positive definite, which is typically the case for structural problems. The basic steps of the conjugate gradient method. 1. Start with an initial guess for the displacement vector u, 0, u, 0, often 0. 2. Compute the residual vector r, k, equals fq, k, r, k, equals fq, k, which represents the difference between the applied forces and the internal forces. 3. Update the displacement vector iteratively by adjusting it in the direction of the residual vector. 4. Repeat the process until the residual vector is sufficiently small, i.e., convergence is achieved. The conjugate gradient method is highly efficient for large, sparse systems, and it can converge very quickly with a well-chosen initial guess. 2. Gauss-Seidel method. The Gauss-Seidel method is another iterative method used to solve systems of linear equations. It is a modification of the Jacobi method, where each element of the displacement vector is updated immediately after it is computed. The method involves the following steps. 1. Start with an initial guess for the displacement vector u, 0, u, 0. 2. Update each displacement component uv, k, uv, k, using the equation uv, k, equals 1 k, phi, j I j uj, k1, uv, k, equals k1 phi, j equals I j uj, k1, where Kk is the diagonal entry of the stiffness matrix corresponding to the ITOF. Phi is the applied force at the ITOF. The summation term represents the contributions from all other degrees of freedom. 3. Repeat the process until the displacement vector converges to a solution. The Gauss-Seidel method is simple and efficient for solving small to medium-sized systems, but it can be slow for larger systems compared to methods like conjugate gradient. 3.3. Handling boundary conditions. Boundary conditions, such as fixed supports or applied displacements, must be properly incorporated into the system before solving for displacements. There are several ways to handle boundary conditions. 1. Elimination method. For fixed DOFs, where displacement is 0, remove the corresponding rows and columns from the global stiffness matrix. Similarly, set the corresponding components of the displacement vector O to 0. This reduces the size of the system and eliminates the need to solve for the fixed displacements. 2. Penalty method. For displacement-based boundary conditions, e.g., a specific displacement at a node, apply a very large value, penalty, to the corresponding entry in the stiffness matrix. This makes the displacement at the constrained DOF very small, i.e., nearly 0, effectively enforcing the boundary condition without modifying the system's size. 3. Lagrange multiplier method. This method is used for incorporating constraints in optimization problems. It introduces additional variables, multipliers, to enforce boundary conditions. 3.4. Post-solution analysis. After solving for the displacements O, you can calculate internal forces and moments in the structure. Use the displacement vector O and the stiffness matrix Kk to compute the internal forces and moments in each element. Finternal equals Q. Finternal equals Q. Deformations and stresses. Based on the displacements and internal forces, you can calculate deformations, strain, and stresses in the structural elements. Solving the linear system Q equals F is a fundamental step in structural analysis, as it provides the displacements of the structure under applied forces. Depending on the size and complexity of the structure, you can choose between direct methods, e.g., Gaussian elimination, Lou decomposition, matrix inversion, or iterative methods, e.g., conjugate, gradient, Gauss-Seidel. Both methods have their advantages depending on the size and sparsity of the stiffness matrix. Once the displacements are determined, further analysis can be done to calculate internal forces, deformations, and stresses, which are essential for assessing the safety and performance of the structure. 3. Matrix methods of structural analysis. Application to frame structures. Frame structures, such as buildings, bridges, and industrial frames, consist of interconnected beams and columns that can carry both vertical and lateral loads. These structures typically experience both bending moments and axial forces, making them more complex to analyze than simple trusses or beams. The matrix methods of structural analysis are particularly useful for analyzing these structures, as they can handle large systems of equations involving many degrees of freedom and multiple types of loadings. The application of matrix methods to frame structures involves using the global stiffness matrix to solve for the displacements and internal forces, bending moments, shear forces, and axial forces in each element of the frame. 3.1. Key characteristics of frame structures. In a typical 2D frame structure, each element, e.g., beam or column, has 6 degrees of freedom per node, 2 translational DOFs, movement in the x and y directions, at each node, 1 rotational DOF, rotation about the z-axis, at each node. Therefore, for a frame structure with nodes, the total degrees of freedom, DOFs, are 3n, because each node contributes 3 DOFs, 2 translational plus 1 rotational. The matrix methods are well suited for handling these types of structures, as the global stiffness matrix must account for both the translational and rotational displacements. 3.2. Steps in matrix analysis of frame structures. 1. Formulation of element stiffness matrices. The first step in applying matrix methods to frame structures is to formulate the local stiffness matrix for each frame element, beam or column. For a 2D frame element, beam or column, the local stiffness matrix CLOCAL is a 6 times 66 times 6 matrix because each element has 2 nodes, and each node has 3 degrees of freedom. The general form of the local stiffness matrix for a beam column element in 2D is CLOCAL equals EIL 126L 126L 6L4L2 6L2L2 minus 12 6L12 6L6L2L2 6L4L2 CLOCAL equals LA 126L 126L 6L4L2 6L2L2 minus 12 6L12 6L6L2L2 6L4L2, where E is the modulus of elasticity, 2 is the moment of inertia of the beam's cross-section, LL is the length of the beam. This matrix relates the forces and moments at the nodes of the beam to the displacements and rotations at the nodes. The stiffness matrix accounts for both axial stiffness, in the direction of the beam, and bending stiffness, due to the beam's moment of inertia. 2. Transformation of local stiffness matrix to global coordinates. For each frame element, the local stiffness matrix must be transformed into the global coordinate system. The local stiffness matrix is formulated in terms of the local axis of the element, usually aligned with the beam, but we need to express the element's behavior in the global coordinate system to form the global stiffness matrix. The transformation matrix TT is used to rotate the local stiffness matrix into the global coordinate system. The general procedure for transforming the local stiffness matrix is global equals global equals where TT is the transformation matrix, which depends on the angle of the element relative to the global coordinate axis. For a 2D frame element, the transformation matrix for an element inclined at an angle to the global axis is given by T equals COS SIN SIN COS SIN COS T equals COS SIN SIN. By applying the transformation, the local stiffness matrix is converted to the global coordinate system. This process allows the global stiffness matrix to represent the overall behavior of the frame structure. 3. Assembling the global stiffness matrix. After transforming the local stiffness matrices for each frame element to the global coordinate system, the next step is to assemble the global stiffness matrix. This is done by placing the individual element stiffness matrices in their correct locations within the global matrix based on the connectivity of the nodes. For example, if a frame element connects node 1 and node 2, the entries of its transformed stiffness matrix are added to the global stiffness matrix KK at the corresponding positions for those two nodes. The assembly process involves superimposing the contributions from all the elements of the frame. This process can be summarized as: for each element, determine which global degrees of freedom correspond to its nodes. Place the transformed stiffness matrix into the global stiffness matrix at the correct positions. Repeat for all elements in the structure. The global stiffness matrix for a frame structure can become quite large, especially if there are many elements and nodes, but the assembly process follows the same procedure regardless of the structure's size. 4. Application of boundary conditions. Before solving for displacements, it is necessary to apply the boundary conditions of the structure. This may include fixed supports, where displacement is 0, or roller supports, where displacement is restricted in certain directions. The boundary conditions are typically handled by eliminating rows and columns corresponding to fixed degrees of freedom from the global stiffness matrix, setting the displacement values at these degrees of freedom to 0 in the displacement vector O, applying large forces or modifying the stiffness matrix, penalty method, to enforce constraints if necessary. 5. Solving the system of equations. Once the global stiffness matrix KK has been assembled and boundary conditions applied, the system of equations Q equals F can be solved for the displacement vector O. This is typically done using direct methods, such as Gaussian elimination or Lou decomposition, or iterative methods, such as the conjugate gradient method. The displacement vector O will provide the displacements, translations and rotations at each node of the frame structure. 6. Calculation of internal forces and moments. After solving for the displacements, the next step is to calculate the internal forces, axial forces, shear forces, and bending moments in each element of the frame structure. This can be done by substituting the displacement values into the element stiffness equation. Finternal equals clocalulocaf internal equals clocaluloccal, where finternal is the internal force vector for the element, which can include axial forces, shear forces, and bending moments. Clocal is the local stiffness matrix of the element. Ulocaluloccal is the local displacement vector for the element. These internal forces can then be used to check the safety of the structure, i.e., ensure that the forces do not exceed the material or structural limits, and to design for proper reinforcement. 3.3. Example: frame structure analysis. Consider a simple 2D frame structure consisting of two beams and a vertical column. 1. Step 1. Formulate the local stiffness matrices for each beam and column element. 2. Step 2. Apply the transformation matrix to convert the local stiffness matrices into the global coordinate system. 3. Step 3. Assemble the global stiffness matrix by summing the contributions of each element's stiffness matrix into the global matrix. 4. Step 4. Apply boundary conditions, e.g., fixed at one end, free at the other. 5. Step 5. Solve the system of equations for the displacement vector O. 6. Step 6. Compute internal forces and moments in each element from the displacements. The matrix methods of structural analysis are highly effective for analyzing frame structures, which are common in civil engineering applications. By applying the global stiffness matrix and solving the system of equations, we can determine the displacements, internal forces, and moments in the structure. This method can handle complex structures with many elements and degrees of freedom, making it a powerful tool in the design and analysis of frames, buildings, bridges, and other structural systems. 4. Finite element method, FEM. Fundamentals of FEM. The finite element method, FEM, is a numerical technique used to solve complex problems in engineering and physics, particularly in structural analysis, heat transfer, fluid dynamics, and more. It divides a large, complicated structure into smaller, simpler parts called finite elements. The method approximates the solution to a problem by solving the system of equations derived from these elements, providing insights into the behavior of the entire structure or system. FEM is widely used in structural analysis because it can handle complicated geometries, boundary conditions, material properties, and loading conditions that are difficult or impossible to solve analytically. 4.1. Basic principles of FEM. The fundamental principles of FEM can be outlined in the following steps. 1. Discretization. The physical structure is divided into a collection of small, simple elements connected at nodes. These elements can be 1D, bars, 2D, shells or plates, or 3D, solids. Each element has its own set of degrees of freedom, DOF, which are usually the displacements at the nodes. 2. Element representation. Each element is described by its stiffness properties, material properties, e.g., Young's modulus, Poisson's ratio, and the shape of the element, e.g., triangular, quadrilateral, or tetrahedral for 2D or 3D structures. 3. Formulation of element equations. For each element, the element stiffness matrix is derived based on the material properties and the geometry of the element. This matrix relates the element nodal displacements to the applied forces. The element stiffness equation is typically Q equals Fa equals Fa, where Ka is the element stiffness matrix, U is the displacement vector of the element nodes. Fa is the force vector applied to the element. 4. Assembly of global system. The next step is to assemble all the element stiffness matrices into a global stiffness matrix Kk for the entire structure. This is done by assembling each element stiffness matrix into the global system based on its node connectivity. The global stiffness matrix represents the relationship between the displacements and forces of the entire structure. Q equals F, where Kk is the global stiffness matrix for the entire structure. O is the global displacement vector. Ff is the global force vector. from all applied loads. 5. Application of boundary conditions. To account for fixed or constrained nodes, boundary conditions are applied by either eliminating the corresponding rows and columns in the global stiffness matrix or by setting the displacement values to 0. 6. Solution of the system. The system of equations Q equals F is solved for the displacement vector O. The solution to this system gives the displacements at each node of the structure. 7. Post-processing. Once the displacements are determined, internal forces, stresses, and strain within the structure are calculated from the displacement field using the element stiffness equations. These can be used to assess the safety, stability, and performance of the structure. 4.2. Advantages of FEM. Versatility. FEM can handle a wide range of problems, from static to dynamic analysis, and from linear to nonlinear problems. Complex geometries. FEM can be applied to structures with complex geometries that are difficult to model using traditional analytical methods. Material heterogeneity. It can account for structures with different materials, each with its own properties, e.g., varying stiffness or thermal conductivity. Boundary conditions. FEM can easily accommodate different types of boundary conditions, such as fixed, roller, or sliding supports. Accurate solutions. The method provides a numerical approximation that can be made as accurate as needed by refining the mesh, i.e., using smaller elements. 4.3. Types of elements in FEM. The choice of element type depends on the type of structure being analyzed. Common element types include 1D elements, beam/bar elements, used for structures like trusses, beams, and rods where bending, shear, and axial forces are important. Example: linear beam elements, e.g., Euler-Bernoulli beam element. 2D elements, plane stress, plane strain, shell elements, used for thin structures, such as plates and shells, which experience bending and in-plane forces. Example: quadrilateral or triangular shell elements. 3D elements, solid elements, used for modeling bulkier structures or objects where all three dimensions play a role in the deformation. Example: hexahedral or tetrahedral solid elements. 4.4. Discretization and mesh generation. Discretization is the process of dividing the entire structure into smaller, manageable elements. The mesh is the collection of these elements and defines the resolution of the model. A finer mesh, more elements, leads to more accurate results but requires more computational resources, while a coarser mesh, fewer elements, reduces computational effort but may lead to less accurate results. The quality of the mesh significantly impacts the accuracy of the FEM solution. Important considerations when creating a mesh include element size. Smaller elements can better capture gradients in stress, strain, or displacement. Element shape. Regular shapes, such as squares or cubes, tend to produce better results compared to irregular shapes. Element refinement. Mesh refinement in regions of high stress gradients or complex geometry can improve the solution's accuracy. 4.5. Solving the system of equations. Once the global stiffness matrix KK and global force vector FF are assembled, the system of equations is solved for the displacement vector O. This can be done using direct methods like Gaussian elimination or LU decomposition for small to medium-sized problems. Iterative methods like conjugate gradient or Gauss-Seidel for large, sparse systems typical in FEM analyses. The solution gives the nodal displacements, which can then be used to compute internal forces, stresses, and strains in each element. 4.6. Post-processing and results interpretation. After solving for the displacements, the next step is to interpret the results. Common post-processing steps include calculating internal forces and stresses. These are derived from the displacements using the element stiffness matrices. Visualizing results. FEM software often provides graphical output such as contour plots of stresses, displacements, and strains, or deformed shape plots showing how the structure deforms under load. Design checks. The calculated stresses and displacements are checked against material properties and design criteria, e.g., strength, stability, to ensure the structure is safe and functional. 4.7. Applications of FEM in structural analysis. FEM is widely used in various areas of structural engineering, including building design, analyzing the behavior of buildings under various loading conditions, e.g., dead loads, live loads, wind, and seismic forces. Bridge design, modeling the forces and displacements in bridges to ensure they can withstand traffic, seismic forces, and environmental conditions. Aerospace structures, analyzing the strength and stiffness of aircraft and spacecraft components under complex loading conditions. Automotive design, evaluating the crashworthiness and structural integrity of vehicles. Geotechnical engineering, modeling soil structure interaction in foundations and tunnels. The finite element method, FEM, is a powerful and flexible tool used to analyze complex structures and systems that cannot be solved with traditional methods. By discretizing a structure into small elements and solving for the displacements and forces, FEM provides a numerical solution that can be as accurate as needed. Its ability to model complex geometries, heterogeneous materials, and various boundary conditions makes it indispensable in modern engineering analysis. 4. Finite element method, FEM. Discretization of structures. The process of discretization is a fundamental step in the finite element method, FEM. It involves dividing a continuous structure or domain, which could be a 1D, 2D, or 3D body, into small, simple elements that can be analyzed using mathematical equations. This step is critical because it transforms a complex continuous problem into a system of smaller, more manageable problems. Through discretization, we approximate the behavior of a structure, and this approximation improves as the number of elements increases. 4.1. What is discretization? Discretization refers to the process of dividing a continuous structure into smaller, finite parts, called elements. Each element is treated as a simple shape with a set number of degrees of freedom, DOFs, which represent the displacements at the nodes, the points where the elements connect. The discretization process involves 1. Dividing the structure into finite elements, e.g., beams, plates, shelves, or solids. 2. Defining the material properties and boundary conditions for each element. 3. Assigning nodes at the corners or along the edges of elements, where the displacements are calculated. The resulting collection of finite elements is called a mesh, and the quality of this mesh directly affects the accuracy and computational efficiency of the analysis. 4.2. Types of elements in FEM. The type of element chosen for discretization depends on the structure being analyzed. Different element types are available for different dimensions and structural applications. 1D elements, line elements, used for structures that primarily experience axial deformation, such as beams and bars. Common types, beam elements, truss elements. These elements are defined by their length, and the DOFs are usually displacements along the axis of the element. 2D elements, surface elements, used for analyzing plates, shells, or structures like walls and thin plates. Common types: triangular or quadrilateral shell elements, plate elements. These elements can capture bending, in plane deformations, and twisting. 3D elements, solid elements, used for modeling bulk structures or objects that experience 3D deformations. Common types: hexahedral, brick elements, tetrahedral elements, pyramid elements. These elements are used to capture the behavior of volumetric structures where all three dimensions of the material contribute to the deformation. 4.3. Process of discretization. 1. Dividing the structure into elements. Discretization begins with dividing the structure into smaller pieces. The method of division depends on the geometry and complexity of the structure. Here are the general steps. Define the geometry. Determine the exact shape and boundaries of the structure or domain you want to analyze. Divide the domain into elements. The structure is divided into small, simple elements. For 2D structures, this might involve subdividing the surface into triangles or quadrilaterals. For 3D structures, the space is divided into tetrahedra or hexahedra. Define the mesh density. The size and number of elements will determine the accuracy of the solution. A finer mesh, with smaller elements, provides a more accurate solution but increases computational cost, while a coarse mesh reduces computation time but may compromise accuracy. 2. Assigning nodes to elements. Nodes are points at the ends or along the boundaries of each element, where the degrees of freedom, displacements, rotations, are calculated. The choice of node placement is critical for ensuring accurate results. In most cases, nodes are placed at the corners of the elements, for 1D and 2D elements, and in 3D elements, they are placed at the corners or along the edges of the element. 3. Defining material properties. Each element is assigned material properties that characterize its behavior under load. Elastic modulus, E, describes the stiffness of the material. Poisson's ratio describes the material's response to axial deformation. Density. For dynamic problems, the material density may be used to calculate the mass matrix. Thermal properties. For thermal analyses, the material properties like conductivity, heat capacity, and thermal expansion may be needed. 4. Setting boundary conditions. Boundary conditions, such as fixed, roller, or free supports, are applied to specific nodes or edges. These conditions are crucial for ensuring that the physical system is modeled realistically. 5. Discretizing loading conditions. For each element, external loads, forces, moments, or pressures are applied. These loads can be distributed over the entire element, or applied at discrete nodes, depending on the nature of the load. 4.4. Types of meshes. The mesh plays a crucial role in determining the accuracy of the solution. There are several types of meshes, which can be classified based on the element shape or the mesh refinement. 1. Structured mesh. A structured mesh is created by dividing the domain into a grid of elements that follow a regular pattern, like rows and columns. It is easy to generate and computationally efficient but works best with simple geometries, like rectangles or squares in 2D, and cuboids in 3D. Advantages: fast to generate, efficient for regular geometries. Disadvantages: limited flexibility for complex shapes. 2. Unstructured mesh. An unstructured mesh uses irregularly shaped elements, triangles or quadrilaterals in 2D, tetrahedra or pyramids in 3D, to fit the geometry of complex structures. It is highly flexible and works well for structures with intricate geometry. Advantages: can handle complex geometries, adaptable to irregular shapes. Disadvantages: more computationally expensive, harder to generate. 3. Hybrid mesh. A hybrid mesh combines structured and unstructured elements. For example, it may use structured elements in regular regions of the domain and unstructured elements in more complex or curved regions. 4.5. Mesh refinement. Mesh refinement is the process of adjusting the size of the elements within the mesh to improve accuracy. In FEM, the results typically improve as the mesh is refined, i.e., by making elements smaller. However, this increases the computational cost. 1. Global refinement. The entire structure is divided into smaller elements, making the elements smaller and more numerous. This improves the solution's accuracy by better capturing the gradients in displacement, stress, or strain. 2. Local refinement. In some regions where there is high variation in stress or deformation, e.g., around a crack or concentrated load, the mesh can be locally refined. This means that smaller elements are used only in critical regions, while larger elements are used in less critical regions. This process is known as adaptive meshing, where the mesh is refined based on initial results or known areas of high interest. 3. Convergence study. To ensure accuracy, a convergence study is performed where the solution is obtained for progressively finer meshes. The results are compared to see when the solution stabilizes, meaning further refinement does not significantly change the results. This helps to ensure that the computational cost is justified by the required accuracy. 4.6. Meshing considerations. When discretizing a structure, certain considerations should be kept in mind to ensure an accurate and efficient analysis. Element quality. Elements should be as close to regular shapes, e.g., squares, cubes, as possible. Irregular shapes can lead to inaccurate results. Element size. Smaller elements, finer mesh, capture the behavior of the structure more accurately, especially in regions with high gradients of stress or strain. However, a finer mesh leads to a larger system of equations and increased computational cost. Geometry compatibility. The mesh should closely follow the geometry of the structure, particularly in complex or curved regions. Boundary conditions and loading. Ensure that the mesh appropriately accounts for boundary conditions and loads. Incorrect mesh alignment with the supports or applied forces can affect the accuracy of the results. 4.7. Example of discretization. Consider a simple 2D beam subjected to a uniform load. The beam is divided into multiple beam elements, e.g., 4 elements. The following steps would be involved. 1. Discretize the beam. Divide the beam into smaller beam elements, e.g., 4 or more elements. 2. Assign material properties. Use appropriate material properties for the beam, e.g., Young's modulus, Poisson's ratio. 3. Define the mesh. Select the mesh size and number of elements. 4. Apply boundary conditions. Define supports at both ends of the beam, e.g., fixed support at one end and roller support at the other. 5. Apply loading. Apply the uniform load along the length of the beam. After discretizing the beam, the FEM analysis will provide the displacements and internal forces, bending moments, shear forces, at each node, which can be used to check the safety and performance of the structure. Discretization is a critical process in FEM transforming complex structural analysis problems into manageable systems that can be solved numerically. The quality of the discretization. The mesh directly influences the accuracy and efficiency of the analysis. A well-designed mesh, along with correct boundary conditions and material properties, enables accurate simulations of a wide variety of structures and systems. 4. Finite element method. FEM. Element types and formulation. In the finite element method, FEM, the entire structure or system is discretized into smaller, simpler parts called finite elements. Each element has a set of governing equations that represent its behavior. The type of element chosen depends on the geometry of the structure, the type of analysis, and the required accuracy. Each element is formulated based on the physical laws governing the behavior of the material and structure, such as Hooke's law for elasticity, heat conduction for thermal problems, or equilibrium equations for structural analysis. The primary goal of element formulation is to derive the stiffness matrix for each element, which is then used to assemble the global system of equations. Let's explore the types of elements commonly used in FEM and how they are formulated. 4.1. Types of elements in FEM. Elements in FEM can be classified by their dimension and application. Below are the common types. 1. 1D elements. Line elements. 1D elements are used for analyzing structures that experience primarily axial deformations, such as beams, trusses, and rods. These elements are defined by their length and can only deform along one axis. Examples: truss elements represent axial deformation in trusses. Beam elements represent bending and axial deformation in beams, taking into account their stiffness and strength properties. Degrees of freedom, DOF. For truss elements, there is typically one DOF at each node, displacement along the axis of the element. For beam elements, each node has 3 DOFs, displacement along the axis, and rotations about 2 axes. 2. 2D elements. Surface elements. 2D elements are used to model structures like plates, shells, and membranes, which primarily experience bending, in plane stresses, and shear. These elements are used in thin structures, where the third dimension can often be neglected. Examples: plane stress elements, used for thin structures subjected to in-plane loading. Plane strain elements, used when the strain in one direction is zero, such as for long structures, e.g., tunnels or dams. Shell elements represent thin-walled structures, capable of modeling bending and membrane action in both directions. Degrees of freedom, DOF. For plane stress/strain elements, each node typically has 2 DOFs, displacement in the x and y directions. For shell elements, each node has 6 DOFs, translations in x, y, and z, and rotations about the x, y, and z axes. 3. 3D elements. Solid elements. 3D elements are used for volumetric structures or solid bodies, where all 3 spatial dimensions contribute to the deformation. These elements are used for bulk structures or volumetric problems, such as pressure vessels, complex 3D components, and other structural bodies. Examples: tetrahedral elements, 4-node 3D elements that are typically used for meshing complex geometries. Hexahedral, brick, elements, 8-node 3D elements commonly used for modeling solid structures. Degrees of freedom, DOF. For 3D solid elements, each node has 3 translational DOFs, displacements along the x, y, and z directions. Depending on the complexity of the element, Additional rotational DOFs may be included for more advanced analyses. 4. 2D and 3D coupled elements. These elements are used for problems where multiphysics analyses are required, such as thermomechanical interactions or electromagnetic fields. These coupled elements incorporate more than one physical effect in their formulation. Examples: thermomechanical elements couple temperature and displacement fields in thermal expansion problems. Piezoelectric elements, used in analyzing structures under mechanical and electrical coupling, e.g., actuators. 4.2. Element formulation. Each type of element requires its own formulation of the governing equations, which is typically done using a process called weak formulation. Here's how the formulation process generally works. 1. Shape functions. A shape function is used to interpolate the displacement field within an element based on the displacements at the nodes of the element. The shape functions are derived based on the geometry of the element and are used to approximate the displacements and stresses throughout the element. For example, in a linear beam element, the displacement between two nodes can be interpolated using linear shape functions, straight lines connecting the displacement at the two nodes. In a quadrilateral plane stress element, higher-order shape functions are used to approximate displacement in 2D, using the displacements at the four nodes. 2. Element stiffness matrix. The stiffness matrix for each element is derived from the principle of virtual work or minimum potential energy. This matrix relates the nodal forces to the nodal displacements. For example, in the case of a 1D truss element, the stiffness matrix is defined as K equals EAL, 1st January 11, K equals Li, 1, 1, 11, where E is the Young's modulus of the material, AA is the cross-sectional area of the element, LL is the length of the element. For more complex elements like shells or solids, the formulation of the stiffness matrix involves integrating the shape functions over the volume or area of the element and taking into account the material properties. 3. Consistent and lumped mass matrices. In dynamic analyses, where inertia is considered, the mass matrix is used to account for the distribution of mass within an element. Consistent mass matrix, derived using shape functions and integrates mass distribution across the element. Lumped mass matrix simplifies the mass matrix by assuming that the mass is concentrated at the nodes, simplifying calculations for large-scale problems. 4. Force vector. The force vector corresponds to the external forces applied to the element, such as distributed loads or point loads. The force vector is calculated based on the external forces and the shape functions of the element. For a beam element with a uniform distributed load, the force vector might look like F equals INTENSITY SHAPE functions equals INTENSITY SHAPE functions. 5. Assembly of global stiffness matrix. Once the stiffness matrix for individual elements is derived, the global stiffness matrix is assembled. This step involves placing the element stiffness matrices into their appropriate positions in the global matrix, based on the element node connections. Similarly, the global force vector is constructed. 4.3. Special elements. Beam and truss elements. These are often used in the analysis of frame structures. They are capable of handling axial forces, bending moments, and shear forces. Shell elements, used for thin-walled structures such as roofs, plates, and shells in 2D or 3D problems. Shell elements can account for bending, membrane forces, and rotational effects. Solid elements, used to model 3D volumetric structures under general loading conditions. Solid elements can capture all 3D formation modes: compression, tension, and shear. Membrane elements, used for structures that carry loads primarily in tension or compression, such as tensioned membranes or cables. 4.4. Example of element formulation. Let's look at the formulation of a 2D linear truss element in more detail. The truss element is assumed to carry axial loads only. No bending. Each truss element is defined by two nodes with 1 DOF per node. Axial displacement. Shape functions. The displacement within the element is interpolated using linear shape functions n1, n1, and n2, n2. U10 equals n1, 10, u1 plus n2, 10, u2 u10 equals n1, 10, u1 plus n2, 10, u2, where u10, u10 is the displacement at any point along the element. u1 and u2 are the displacements at the two nodes. Element stiffness matrix. For a linear truss element, the stiffness matrix is K equals EAL, 1st January 11, K equals Li, 1, 1, 11, where E is Young's modulus, EA is the cross-sectional area, LL is the length of the element. Global stiffness matrix. When assembling the stiffness matrix for multiple elements, we place the local stiffness matrices into the global matrix based on the connectivity of nodes. The type of element used in FEM depends on the structure's dimensions and behavior, as well as the specific goals of the analysis. The formulation of the elements is based on physical principles like elasticity, strain displacement relationships, and equilibrium equations. Each element type, 1D, 2D, 3D, has its own unique formulation, but they all contribute to the overall solution of the structure by providing a set of equations, stiffness matrices, force vectors, that describe the behavior of the individual elements within the global system. The correct formulation ensures that the FEM analysis accurately captures the response of the entire structure. 4. Finite element method. FEM. Assembly and solution procedures. Once individual finite elements have been discretized, formulated, and their stiffness matrices and force vectors derived, the next steps in the finite element method, FEM, involve assembling these individual element matrices into a global system and solving for the displacements and internal forces of the entire structure. The process can be broken down into the following major steps. 4.1. Assembly of the global system. 1. Nodal connectivity and global degrees of freedom, DOF. The first step in the assembly process is to determine the global degrees of freedom, DOF, of the system. The DOF corresponds to the number of unknowns, typically displacements or rotations, that need to be solved for at each node. For a 1D truss element, the DOF at each node is typically a single displacement along the axial direction. For a 2D plane stress element, each node has two DOFs, displacements in the x and y directions. For 3D solid elements, each node has three DOFs, displacements along x, y, and z directions. The global DOF corresponds to all the displacements, or rotations, at the nodes in the entire structure. 2. Global stiffness matrix. The global stiffness matrix, KK, is constructed by assembling the individual element stiffness matrices. This involves placing the contributions from each element stiffness matrix into the appropriate positions of the global stiffness matrix based on the nodal connectivity. For example, The stiffness matrix of an individual element, kk, is mapped to the global matrix Kk by using the nodal numbers of the element. Each element's stiffness matrix affects the rows and columns of the global matrix corresponding to the element's nodes. 3. Global force vector. The global force vector, FF, is assembled in a similar manner as the global stiffness matrix. Each element contributes to the global force vector based on the external loads or forces applied to the nodes. For example, if an external load is applied at a specific node in a truss element, that load will be included in the corresponding position of the global force vector. 4. Applying boundary conditions. Boundary conditions must be applied to the global system to represent constraints such as fixed supports, rollers, or prescribed displacements. The assembly process is modified when applying these boundary conditions. Fixed supports impose zero displacements, e.g., u equals 0, u equals 0. Prescribed displacements may apply specific displacements to certain nodes, e.g., u equals 2, u equals 2. Rollers and hinges can apply constraints in certain directions, e.g., a roller restricts movement in the y direction but allows movement in the x direction. The global matrix Kk and the global force vector FF are modified to account for these boundary conditions by eliminating rows and columns of Kk and adjusting FF accordingly. 4.2. Solution of the system of equations. Once the global stiffness matrix Kk and global force vector FF are assembled, the primary goal is to solve for the unknown displacements, O, of the system. The fundamental equation governing the system is Ku equals F, Ku equals F, where Kk is the global stiffness matrix, O is the displacement vector, unknowns, FF is the global force vector. 1. Solving for displacements. To find the displacements, we need to solve the system of linear equations. U equals K1F, U equals K1F. However, for large and complex systems, directly inverting Kk is computationally expensive. Instead, numerical methods are typically used to solve this system. The two most common methods for solving this system are Gaussian elimination. This direct method solves the system by reducing it to a simpler form, usually triangular, and then back substituting to find the displacements. This is suitable for small to moderately sized problems. Iterative methods. For large systems, iterative methods such as the conjugate gradient method, Gauss-Seidel, or Jacobi methods are used. These methods iteratively approximate the solution and are more computationally efficient for large systems where direct methods are impractical. 2. Solving for internal forces. Once the displacements are obtained, the internal forces in the structure, e.g., axial forces, bending moments, can be calculated. The internal force vector Φ can be derived by multiplying the element stiffness matrix with the calculated displacements. Φ equals KEUE Fint equals KEUE, where kk is the stiffness matrix for an element and UA is the displacement vector for that element. For each element, this can give the reaction forces at the nodes, which can then be used to assess the structural performance under the applied loads. 4.3. Post-processing. After solving for the displacements and internal forces, the following steps are typically performed to interpret and visualize the results. 1. Stress and strain calculation. Stress and strain are typically derived from the displacement results. For example, in a truss element, the axial stress can be computed using Hooke's law, equals Fa equals F, where Ff is the internal axial force, and Aa is the cross-sectional area. Similarly, For more complex elements, like beams or shells, the strain and stress can be derived from the displacement gradients. 2. Deformation visualization. The displacements are used to compute the deformed shape of the structure. Often, the results are displayed in graphical form, where the deformed shape is shown, often exaggerated to highlight the displacement magnitudes. This provides valuable insight into how the structure behaves under loading. 3. Checking for structural integrity. The results are analyzed to check whether the stresses, displacements, or strains exceed acceptable limits. This is important for design and safety considerations. Stress analysis. Check if the stress in any part of the structure exceeds the material's yield or ultimate strength. Deflection limits. Ensure the displacements are within permissible limits based on design codes or safety requirements. 4.4. Example procedure. Simple beam analysis. Let's walk through a simplified FEM solution procedure for a cantilever beam with a point load at the free end. 1. Discretize the beam. Divide the beam into several finite elements, e.g., 2 to 4 beam elements depending on the desired accuracy. 2. Formulate the element stiffness matrices. For each element, derive the stiffness matrix using the beam element formulation, e.g., Euler-Bernoulli beam theory. 3. Assemble the global stiffness matrix. Using the connectivity of the elements, assemble the individual element stiffness matrices into the global stiffness matrix. 4. Apply boundary conditions. Apply the boundary conditions at the fixed end of the cantilever beam, e.g., displacement at the fixed node is 0. 5. Apply external load. Apply the point load at the free end in the global force vector. 6. Solve for nodal displacements. Solve the system of linear equations for the unknown nodal displacements. 7. Calculate internal forces. Using the calculated displacements, compute the internal forces, e.g., bending moments, shear forces. 8. Post-process the results. Visualize the displacement of the beam and check the stress distribution to ensure the design meets safety requirements. 4.5. Conclusion. The assembly and solution procedures in FEM are critical steps in obtaining meaningful results for structural analysis. The assembly process involves creating the global stiffness matrix and force vector by combining the contributions of individual finite elements, considering the nodal connectivity and boundary conditions. The solution process then solves for the unknown displacements and internal forces using numerical methods. Finally, post-processing provides a means of interpreting the results, checking the integrity of the structure, and ensuring that the design is both safe and functional. These procedures are foundational to applying FEM in engineering analysis and design, and their efficiency and accuracy are paramount in solving real-world engineering problems. 4. Finite element method, FEM. Applications to structural problems. The finite element method, FEM, is widely used in engineering to analyze and solve complex structural problems that are difficult or impossible to handle using traditional analytical methods. FEM is particularly valuable when dealing with intricate geometries, material properties, boundary conditions, and loadings. Below, we will explore several key applications of FEM to structural problems. 4.1. Structural analysis of beams and frames. 1. Beam analysis. FEM can be used to analyze beam structures under various loading conditions, including uniform loads, point loads, and moments. The method provides a way to evaluate deflections, bending moments, shear forces, and stress distributions in both simple and complex beam geometries. Application example: a cantilever beam subjected to a concentrated load at the free end. FEM can be used to calculate the deflection at the point of loading, the distribution of bending moments, and the resulting stresses at various points along the beam. Benefits: ability to model non-uniform cross-sections. Nonlinear behaviors, such as large deflections or plastic deformation, can be accounted for. Can analyze the beam's dynamic response under time-dependent loads, e.g., vibrations. 2. Frame analysis. For frame structures, which consist of beams and columns, FEM allows the calculation of axial forces, bending moments, shear forces, and deflections throughout the structure. This is important for multi-story buildings, bridges, and industrial structures. Application example: a high-rise building with wind or seismic loads. FEM can help evaluate how the frame behaves under lateral forces, determining whether the columns and beams are adequately sized to handle these loads. Benefits: accurate modeling of complex frame geometry. Can handle mixed boundary conditions, fixed supports, roller supports, and pinned connections. Can simulate the interaction between different parts of the structure, e.g., beams and columns. 4.2. Stress analysis of plates and shells. 1. Plate structures. FEM is ideal for analyzing thin, flat structures like plates, where bending and in-plane forces are significant. Plates may experience various load types, including uniform pressure, point loads, or bending moments. Application example: analyzing the deflection and stress distribution in a large concrete slab subjected to uniform loading, e.g., a floor slab or a foundation plate. Benefits: ability to model arbitrary shapes and boundary conditions, e.g., simply supported or clamped edges. Can account for bending, shear, and membrane forces in a single solution. Enables detailed analysis of stress concentrations around holes, cutouts, or discontinuities. 2. Shell structures. Shells are thin structures where bending, membrane forces, and torsion are important. FEM can be used to analyze shell structures, such as roofs, tanks, and aerodynamic panels in aerospace engineering. Application example: a dome structure or aerospace fuselage. FEM can evaluate how the structure deforms under external pressure or aerodynamic forces, including the stresses and strains in the shell. Benefits: complex geometries, curved surfaces, varying thickness, can be easily modeled. Can handle nonlinear effects such as large deformations or material yielding. Used for vibration analysis to determine the natural frequencies of shell structures. 4.3. Truss and structural frame optimization. 1. Truss optimization. FEM is also employed in the design and optimization of trusses, which are commonly used in bridges, towers, and other lightweight structures. The goal is often to minimize material usage while maintaining structural integrity. Application example: bridge trusses or overhead transmission line towers. FEM can evaluate the internal forces, tension and compression, in the truss members under various loading conditions to ensure optimal design. Benefits: can optimize the geometry and material distribution of the truss elements to minimize weight and cost. Ability to perform linear and nonlinear analysis of truss stability, e.g., buckling analysis. 2. Structural frame optimization. FEM can optimize entire structural frames, including their material properties, geometry, and joint connections, to meet specified criteria like load-bearing capacity, stability, and cost. Application example: high-rise building frame optimization to reduce material usage while ensuring that the frame meets the required safety standards under seismic or wind loads. Benefits: parametric optimization allows for design adjustments based on different load scenarios or constraints, e.g., weight reduction, cost reduction. Can accommodate complex geometries and irregular load distributions. 4.4. Thermal stress analysis. In many structural applications, temperature variations can induce thermal stresses, which can affect the overall stability and performance of the structure. FEM is commonly used to model thermal stresses in structures that experience temperature changes, such as bridges, dams, pressure vessels, and piping systems. Application example: analyzing the thermal expansion in a pressure vessel subjected to heating and cooling cycles, which could lead to thermal stresses and deformation. Benefits: coupled thermal mechanical analysis allows the simulation of both thermal effects and their impact on mechanical behavior. Accounts for nonlinear material properties, thermal expansion coefficient, and temperature-dependent material properties. Can model non-uniform temperature distributions, such as those from external sources or internal heat generation. 4.5. Seismic analysis. FEM is used extensively in earthquake engineering to evaluate the seismic performance of structures. This includes dynamic analysis to predict how a structure will behave under earthquake loads, which vary with time and frequency. Application example: seismic analysis of a tall building. FEM can simulate how the building will respond to earthquake ground motions, allowing for evaluation of the dynamic response, including displacements, accelerations, and forces at each floor. Benefits: allows for the evaluation of resonance frequencies, which can lead to amplification of seismic waves if matched with the structure's natural frequencies. Can predict local failures, e.g., floor collapse, wall cracking, or global instability, e.g., building overturning. Helps optimize damping systems, e.g., tuned mass dampers, to reduce the structural response during earthquakes. 4.6. Nonlinear structural analysis. In real-world applications, many structural components exhibit nonlinear behavior under loading conditions, e.g., large deformations, material yielding, plasticity. FEM is capable of modeling both geometrically nonlinear and materially nonlinear behaviors. 1. Geometrically nonlinear analysis. This type of analysis considers large deformations, where the displacement of the structure is large enough that the assumption of small deformations no longer holds. Application example: analyzing the buckling behavior of a column under compressive load, or evaluating large deflections in a beam under heavy loading. Benefits: accurate prediction of instabilities such as buckling, snap-through, or post-buckling behavior. Can simulate large deformations without linear assumptions. 2. Material nonlinear analysis. In material nonlinear analysis, the material properties of a structure are assumed to change with stress or strain. This can include plasticity, creep, or viscoelastic behavior. Application example: evaluating the plastic deformation in a steel frame under extreme loading, e.g., a building exposed to a blast or heavy impact. Benefits: accounts for yielding and plastic flow beyond the material's elastic limit. Models failure criteria, such as the onset of cracks or material rupture. 4.7. Fatigue and fracture analysis. FEM can also be used to assess the fatigue life of structures subjected to repeated loading and to simulate the progression of cracks or fractures under dynamic or cyclic loading conditions. Application example: fatigue analysis of an aircraft wing, which is subjected to repeated aerodynamic loads and pressure cycles. FEM can help predict where cracks may initiate and how the structure will fail after a certain number of cycles. Benefits: helps to predict the life expectancy of components under cyclic loading. Enables design adjustments to improve fatigue resistance, such as material selection, geometry changes, or load redistribution. The finite element method, FEM, is a versatile and powerful tool in structural engineering that enables the analysis of a wide range of structural problems, from simple beam deflections to complex 3D structures subjected to nonlinear, dynamic, or seismic loading conditions. FEM is invaluable for optimizing designs, ensuring safety, and improving the efficiency of structural systems. Its ability to handle complex geometries, varied material properties, and different loading conditions makes it indispensable for modern engineering applications. Dear viewers, we would like to extend our heartfelt thanks to each of you for patiently watching this video until the very end. Your time and attention are greatly appreciated, and we hope that the content has been enriching and insightful for you. For those eager to continue, we are pleased to inform you that the next part of this video will be available. Please find the link in the description section below to continue your journey with us. Thank you once again for your support, and we look forward to having you with us as we explore more together. Warm regards. Trine Biblical University Global Extension, USA.